mute your microphone, and also please turn off your video. If you have any query or question regarding the talk, you need to write it in the chat box of Webex meeting. And after the completion of the talk by Dr. Michael Cifra, he will address those questions in the time allotted for question answer session. Now, I would like to invite our IEEE volunteer, Mr. Kumar Mohit, to give brief introduction of Dr. Michael Cifra. Kumar.
Thank you, Vivek sir. Good evening, ladies and gentlemen. A heartiest welcome to all of you. Today, we at IEEE MNIT Student Branch are privileged to welcome our speaker for today, Dr. Michael Cifra. Dr. Michael is known for his work in the field of bioelectrodynamics, bioelectromagnetics, nanosensors, microtubules, biosignals, biological electron excited states, and ultraviolet photon emission, which makes him the perfect man for presenting on today's topic, which is engineering electromagnetic devices based on biophysical insights for future medicine. Dr. Cifra is a distinguished name in the scientific community in the field of bioelectrodynamics. Sir has received his MSc in 2006 in biomedical engineering from University of Zelina, Slovakia, and PhD in 2009 in radio electronics from Department of Electromagnetic Field, CES Technical University in Prague. He is the IEEE senior member and chair of EMB chapter of the IEEE Czechoslovakia section and is a head of bioelectrodynamics research team and senior scientist at the Institute of Photonics and Electronics of the CES Academy of Science. Apart from this, Sir also holds membership of URSI, AAAS, Bioelectrochemical Society, Bioelectromagnetic Society, European Microwave Association, International Society for Bioelectromagnetism, IUPAC, to name a few. Sir has been project head and has led many teams in accomplishing projects, some of which are radio frequency characterization of microtubules using micro and nanosensors, photonic measurement and characterization. Currently, Sir and his team is working on the project Nanosecond Electric Pulses for modulation of microtubule dynamics. Sir also has been part of many publications in the field of electrodynamics since 1997. Dr. Michael holds international research experience at International Institute of Biophysics, News, Germany, visiting researcher, National Institute of Material Science, Tsukuba, Japan, and visiting professor, James Franck Institute, Department of Chemistry, University of Chicago, USA. Awards and honors are the gems which makes the qualities of a person shine, and Sir's profile sparkles with many awards and honors such as Otto Witterl Award from the CES Academy of Sciences in the field of mathematics, physics, and earth sciences, European Molecular Biology Laboratory, Advanced Training Center, Corporate Partnership Program Fellowship, URSI Young Scientist Awards, to list a few. Such experience, knowledge, and achievements is a stake worth inspiring, and literally we can go all day listing them. So rather, now I would like to welcome and request Dr. Michael Cifra to take the mic and enlighten us. Sir, please. Thank you.
Thank you very much for such a extensive introduction. I really appreciate it, and I also really appreciated you all take your time. And actually, I'm seeing now more than 50 participants, so it's a great honor to me. I thanks a lot to Professor Tripathi for inviting me, and also to other colleagues from the branch for organizing this. So thank you again very much. And I hope that you all can see my screen, and I will be starting now. So as I've been introduced, I am one of the team leaders of the research teams at the Institute of Photonics and Electronics, which is seated in Prague, Czech Republic, in Europe. And in our institute, we have several research teams, and most of the research is oriented in electromagnetics, photonics, but we have a lot of interdisciplinary application of this research. And basically, the team which I lead is proof for this. So let me first start with kind of story. So I'm wondering if some of you know where this image comes from, what kind of movie is it? Well, I will give an answer to you. So some of you might be familiar with the Star Trek series, science fiction movie, which I'm a big fan since my childhood. And I was always very intrigued to see these interesting devices which can somehow wirelessly, non-contactly probe what is happening in the organism and also influence the organism in some simply non-contact way. So this is kind of inspiration for me also in my research through my life, in my career. And these devices in these science movies, in Star Trek, they are called tricorders. So basically these are kind of devices which can non-contactly diagnose and heal diseases. So the question is, are we any close to these medical tricorder technologies currently? I will show you some recent results from our lab. What you see here is the fluorescence image of several animal cells. Specifically, these are osteosarcoma cancer cells. And now, if we send to these cells a particular electric pulses or electromagnetic pulses, what we can see that these cells quite change their shape and structure, which is very intriguing. So somehow we have here a physical tool, electromagnetic radiation, electromagnetic pulses, which can principally also non-contactly affect the biology and physiology of the living cells, which are the basic units of organism. So in short, to introduce our team specifically, this is us currently. So we are a bunch of people from various backgrounds, including microwave, electrical engineering, but also biophysics and physical chemistry. The mission of our team is to probe and influence biomolecular systems, including organisms, using electromagnetic field. The vision, which is guiding us, is to develop novel electromagnetic methods which would bring us closer to a world where we have more efficient and also gentler and more benign medicine and nanotechnology. The tools which we use to accomplish our mission vision is advanced electromagnetic concepts, different various micro and nanotechnology enabled tools, and also computational methods. We try to start, as in good research, with a solid theory. So we develop theory of passive and active electromagnetic properties of biological systems, where under passive electromagnetic properties of biosystems, I mean how external electromagnetic field affects biological systems, and under active, what I mean how biological systems, how organisms can actually generate their own endogenous electromagnetic field. These theories gives us specific predictions to develop new devices and technological experimental platforms which rely on electromagnetic design and micro nanofabrication I mentioned earlier. And once we have suitable devices and experimental platforms developed, we then verify our theories and experiments. So basically, we focus mostly on cells, living cells, and subcellular structures in our experiments. This is to kind of give you a visual artistic picture of how we perceive organisms. So organisms are very complicated and complex machines, so to say, but we do not rely only on a mechanistic understanding of the biophysics and science. Actually, what we believe is important is that we embrace both mechanistic and integrative science philosophy. So we believe that to understand the whole, we need to understand the parts, but also the interaction of the parts. Now, when I bring it this general philosophy, scientific philosophy to particularities of our research, what we actually do, we basically disassemble the organisms to its individual parts, biomolecular components, and try to reconstitute the function of organisms, and then to see how these individual parts and reconstituted structures of organisms respond to electromagnetic field. So in our particular case, we focused on mostly focused on the parts of the cells, which are called microtubules, these kind of tubes, which you can see on the right. So why do we focus on microtubules? So here on the left, you can see a scheme, simple graphical scheme of a biological cell. You can see roughly the dimensions of this. And you can see that in the cell there are different types of fibers or structures. This is very general. Every cell has this kind of cellular skeleton or cytoskeleton. And these particularly microtubules are a very important part of the cytoskeleton because they enable cell to divide. They enable also intercellular transport, intercellular signaling. But why are they interesting, these microtubules, from an electrical perspective? Is because tubulin, the subunit of these microtubules, of these red tubes, which have nanoscopic diameter, this tubulin has very high electric charge and dipole moment, which make it particularly susceptible to external electric and electromagnetic fields. So cytoskeleton and microtubule is not a static structure. Actually, depending on your bandwidth, if you can see this video, you can see that in the real time, what happens all the time in the cell is that the microtubules, they assemble or grow, and after a certain period of time they can disassemble or basically fall apart, and this enables plasticity of the biological function in the cell. That's how a cell can change their shape, for example. Now, the content of my talk today after this interaction has basically two parts. One is why and how we can understand the complex permittivity of biomolecule solutions. And the second part will be on how the pulsed electric field can be used for modulating function of biosystems. So at first, let's start with the understanding of permittivity. So those who are familiar with the basic of the physics and electromagnetic physics, you probably know all very well the permittivity or dielectric constant, so to say, determines how electric field interacts with material, be it inanimate or animate living material. And since most of the interaction of the electromagnetic field is through its electric component with the biomaterial, that's why permittivity is much more important than the magnetic permeability. So the permittivity is in general complex mathematical quantity, and it, as mentioned, it determines how strongly material interacts with the electric field. So why do we need to understand this complex permittivity? Well, we need to have the best knowledge possible about the complex permittivity of biomaterials and tissues, because only then we can develop novel electromagnetic therapeutic and diagnostic methods. So we need first to have understanding which is theoretical, that's computational tools, which I'm going to speak briefly, and also about the experimental tools. So why do we need to understand, let's say, more from a theoretical and modeling perspective, what is the complex permittivity of biomaterials? Well, because only then, when we understand how complex permittivity and its values are generated from the molecular structure, we can predict complex permittivity to rationalize selection of appropriate frequencies for microwave therapeutic and diagnostics. But also we need to have a good understanding in order to interpret the complex permittivity of the biomaterials which we already measured. I will introduce you now one method which is rather new, and this method is based on a simulation of molecular dynamics. So basically these kind of simulations employ classical physics and employ Newton equation for determining the motion of every atom. So for this method, one need to have knowledge, a priori knowledge about molecular structure, which is now available in many databases. So, for example, when I know that my sample contains proteins and water, I can employ these methods, but I need to have an a priori knowledge of that. And this method is very powerful and is now used in many methods in biophysics and also applied physics. And for us, it's important that it enables us to understand how macroscopic dielectric properties arise from molecular structure and dynamics, and then how electromagnetic field can exert its effects on the biomolecular level. So practically how this method works. So first one runs molecular dynamic simulations. There is a lot of freeware available on that on online, which you can find. So here you can see, I give you a simple example. Here you can see on the nanoscopic level, the stochastic motion of water molecules, these small triangles, red and white, which are in the background, and few simple biomolecules here. It's alanine, an important component of the proteins, which are present basically building parts of our bodies. So here you can see the fluctuating motion of these molecules, and what we did here, we increased the concentration of these alanine molecules. So you can see there are more of them here and more of them here. Now, what you can also see is this blue arrow, which is a fluctuating dipole moment. And this is the quantity which we can quantify, which we can analyze in these simulations, and then take autocorrelation function of this dipole moment. And based on that, we can calculate the susceptibility, which is directly related to complex permittivity of these biomaterials. So for the molecular structure, we can predict the permittivity, which is the measurable quantity. Based on this, we found some interesting new data. I will just make this short. I will not describe these graphs in details, but what you can see is a real part, an imaginary part of the complex permittivity in microwave band. And what we found, and this is what is interesting for this integrative understanding, that the biomaterial properties, like also electromagnetic properties, like complex permittivity, they arise not only from as a sum of the parts, but also what is important here is that the interaction between individual parts, in this case, it's water molecules and biomolecules. The interaction between biomolecules and water molecules also contribute to the electromagnetic response. This is shown in these graphs here, and when you can see that the cross correlation contribution of water and alanine is becoming very important for physiologically important concentrations. And what is important that these molecular dynamics actually enables to understand, to dissect, so to say, individual contributions of particular phases. I mean, by phases we mean water and biomolecules, and how they contribute to complex permittivity. So now, having this theoretical understanding of how molecular structure bring about complex permittivity of biomaterial, we also need to have an experimental tools to verify these computational modeling and predictions, and also to measure to measure the complex permittivity as such. So there is one challenge here, and that's that many precious biosamples, either being direct samples from a patient, for example, or the samples of purified proteins, for example, those which we use, can be very expensive, literally speaking. For example, the 10 milligrams of proteins which we use can cost up to $1,000 US dollars. So you can imagine these samples can be very expensive. So we cannot afford to use large volumes. And currently, the commercial solutions only offer measurement from large volumes. So we need to develop experimental tools which will enable us to measure permittivity from smaller volumes. So in short, we developed for this purpose of measuring permittivity and sensing using microwaves, we developed various resonant devices and also broadband devices. And in the following, I want to focus on our recent work, which was recently accepted and this to the publication. And this is the work on the microstructured on-chip coplanar waveguide for nanoliter volume analysis. So I will show you briefly the story of the paper. So I already introduced you these microtubules, which are, you can understand them as a dynamic bones of the living cells. Now, this property of polymerization and the depolymerization of growing and of shrinking of these microtubules is very important in drug discovery and drug research, and also for cancer therapy. So it's very important to have a swift and methods how to analyze the state of the polymerization. So if the microtubule is one tube or is decomposed to individual components, these tubulin heterodimers. So the challenge here, the goal is here to try to see if microwaves can be used to detect unpolymerized versus polymerized state of these components of the cell. The current methods which are available has some disadvantages. So mainly the typical method of light scattering, which is used currently in the laboratories to measure microtubule polymerization, they are not easily integrable on chips and have also rather low contrast for small samples. The viscometry methods require large bulk samples. Now the question is if using microwaves and integrating the microwave to sense the content of the small microscopic fluidic channels, so in short microfluidics, could resolve these drawbacks of the current methods. So the advantages would be that we could use very small volumes, and we could integrate these on chips. You know that microwave circuits are now easily integratable on chips. The proof of it is our mobile phones and cell phones. But there are also some cons. Currently, these measurements would require a vector network analyzer, which can be circumvented in future using only a few frequencies for measurement. So what is now this is important part. Typically engineers would just jump in and design a device somewhere, maybe 2.4 gigahertz, because it's easy and there are many circuits to do it readily. But I would like to think about before any design you as an engineer you would perform is to ask, so why is this the frequency I would like to use it for sensing? Why is this frequency useful for, or why is it useful for affecting the biological systems or organisms? Why exactly is this frequency? Because this is very important. What are the frequency bands? So basically what I'm going to show you is how to, an example, how the engineering requirements for a device can be rationalized by having insights from other fields like biomedicine or biophysics. So in our case, the hypothesis is as follows. We know that the polymerization of these small components into microtubules changes viscosity of the solution. Now, viscosity eta here affects the rotational diffusion of the molecules. Any molecules in this solution will be affected by changing of viscosity, and that will perturb the central frequency of the imaginary part of the permittivity. Now, if we want to focus on a most common component of tissues and organisms, then it's actually a water molecule. So water molecule has a rotational diffusion time constant and corresponding frequency of around 20 gigahertz. So if there will be change of permittivity, we would be expecting the change of the frequency of the imaginary part of the permittivity around this frequency. So in short, this change of the permittivity, change of the viscosity will affect the permittivity through this debye model, and that will tell us that we should be optimizing the frequency of operation in the broadband, because we need to see this effect on the broadband. So that will be giving us a requirement of operation frequency from 1 to 50 gigahertz at the first iteration. So what we did to achieve this, we did the following. We followed the strategy I'm showing on this image. So on our microfluidic system, we inserted either the unpolymerized tubulin and then the polymerized or the self-assembled microtubules, and we wanted to see if microwave transmission, which is given now by S parameters, will be different for tubulin compared to microtubules. So I will show you first the design of our chip. Our chip is basically a series of very small microscopic transmission lines, microwave transmission lines, which are fabricated on a quartz glass substrate on the and using the thin film deposition technology and laser lithography. So you can see the dimensions of our coplanar waveguide, which will serve as a sensing chip. And on top of that, we integrated a microfluidic channel with the inlet and outlet, and we let our samples flow just above this transmission line and trying to see if these polymerized versus unpolymerized microtubules can be distinguished. So the fabricated chip looks like this. So you can see it's basically a piece of nice glass with some gold metal patterns fabricated in our lab. And this is our measurement setup. You can see our vector network analyzer. The connection to the chip was done by these ground probes, and this is on a. You can see the image of the channel under microscope here. So you can see that the channel is only roughly 70 micrometers wide. That's where we flow our sample through, and you can see the S parameters measured at the same time in here at the vector network analyzer. So what we found that actually, indeed, yes, we are able to distinguish the free tubulin, which is not polymerized, not assembled between the microtubules. So actually, we can see these differences of one sample towards other in S parameters through the broad band, as we expected. And based on this, and the rigorous model, electromagnetic model, which we prepared in CST software, we could also extract permittivity of buffer solution, also of the tubulin and the microtubules. So in short, we were able to predict that microtubules should be able to distinguish the assembled or disassembled bones of the cell, cytoskeleton. And based on these predictions, we designed in particular frequency bands, the microwave sensing chip. And also we were able to not only distinguish these states using microwaves, but also to extract the permittivity of these samples. So now the second part will be a shorter and faster one, is around how we can use very short pulse electric field to affect biological systems, how that could potentially be used for future biomedicine. So in short, currently since 30 years, biomedical and biophysical fields use rather long, here I mean long is microsecond and millisecond pulses to manipulate the cell structure by the following way. You can imagine that a cell, here is a simple image, simple scheme of the biological cell, has a cell membrane and a cell nucleus. You can, being an engineer, you can make an equivalent circuit of this with capacitors, mostly capacitors and resistors, which represent individual parts of the cell. And when this cell is placed in its liquid medium between the electrodes, you can also have these, all of these represented by electrical circuit. Now, why is it the case that, for example, membranes are capacitors? Because they are the capacitors because they have these membranes are basically not conductive, electrically non-conductive, thin layers of few nanometers, and also here during the cell living, when the cell is alive, there is a permanent electrical potential difference between two sides of these membranes, What does it mean electrically is that there is slightly, apparently slightly more positive charge outside and slightly negative charge inside. Now, when we put this electrical object, a biological cell, in the electric field, what happens with a certain time scale is the polarization of the further polarization of these membranes, which is largest at the poles close to the electrodes, which is given by the radius vector of the cell and the vector of the electric field. And then what happens is that at these parts, mostly when exceeding certain threshold, electric field strength threshold, the cell membrane will undergo basically a dielectric breakdown and the cell pores will be created. So this is electroporation, which is now used in many fields in biotechnology and molecular biology, and also now in clinical applications such as in cancer therapy, where the drugs can be delivered selectively only to the cells which are electroporated. Now, what we're interested in our lab are especially shorter pulses, nanosecond pulses. And for different reasons, in literature, it has been demonstrated already that these nanosecond pulses, electric pulses, can not only pour a membrane, which can be done also by longer pulses, but also these pulses affect the internal parts, internal structure of the cell with various effects. And particularly, some breakdown of cytoskeleton of this dynamic skeleton of the cell has been observed as well. Now, I will show you again why these nanosecond electric pulses are interesting for modulation of cellular function, as particularly the function of the cytoskeleton of the cell, and how we can understand the effects from atoms to the larger structures. So at first, why are nanosecond pulses interesting from different perspectives? So using only very short electric pulses, that means on time scales of a few nanoseconds or a few tens of nanoseconds, one can apply very high field strengths without heating the sample. We want to avoid thermal effects because they have also many side effects. And this is important. So that's in order to achieve strong electric field without heating, this can be done by having very short pulses. Now, as a consequence of pulses being short, they have a rather broad spectral content, which spans, depending on the pulse shape and pulse duration, span up into the radio frequency band. So that's why dealing in engineering devices for these pulses requires RF and microwave engineers. Now, why is this important? These short pulses from a molecular perspective, these high field strength, which are achievable with pulse electric field, can overcome thermal forces and can act directly on the molecular structure by mechanical force, because all these biomolecules have charges which electric field can act upon and basically move them by mechanical force, electromechanical. And importantly, since these electric pulses are short, it is possible to make predictions of how all of these atoms move, because these short nanosecond scale simulations are computationally feasible, in contrast to millisecond and second simulations, where it's impossible to model with current computational power available in the world to model the movement of all atoms. So what we did, we first asked the question, how short electric field, like short duration electric field, affects the components of the cytoskeleton of these tubulins, these individual balls which can self-assemble to microtubules. So we made computational in silico predictions. So what you can see here is a single protein molecule of a tubulin, here for 0 megawatts per meter, 20 megawatts per meter, and 100 megawatts per meter. And this, you can see what is the size of this molecule. So it's really a nanoscopic system. I don't show any water around, just to make it easy to see. But you can see here that while for no electric field, the molecule only tumbles around by thermal motion. When the field is strong enough, this is the electric field vector, the dipole moment, orange arrow, aligns with the electric field. This is what happens to molecules. So electric field can actually align dipole moments of individual molecules as long as dipole moment is large enough, which is the case for this tubulin. If the field strength is even higher, within a few nanoseconds, even the structure of this protein changes. So the message is here that actually electric field can change the structure of the molecules if the electric field is strong enough, even in few nanoseconds. So what we found is that the shape of this molecule changes, the dipole moment of this tubulin of this molecule is affected, and also the functional important structure of this tubulin can be affected by electric field. So this all is computational simulation. The question is this happening actually in reality? So this is where experiments come in. And what we did, we took these isolated biomolecules, this tubulin, and we exposed them to electric pulses. So basically performed experiment outside of the cell in vitro. That means in vitro in Latin. So these are the parameters of the electric pulses which we used. And then we characterize, after we apply these tubulins in the tube, electric fields to these molecules in a simple test tube, then we characterize this tubulin by different methods, and we then try to polymerize these tubulins to microtubules. So this was a major discovery which we did in past few years. We found that the electric pulses, after being affected by, we found that the electric pulses affect this tubulin by changing its conformation temporarily, and this leads to change kinetics of how these individual balls, these molecules, self-assemble to larger structures. And they found that these electric pulses affect what kind of structures are actually created from the individual building blocks. So while non-treated tubulin molecules self-assemble into the tube, which you've seen earlier, the electric field treated tubulin self-assemble to different structures. So basically, the electric field can act as a non-chemical effector of a biomolecular function, which has implications for biology. So in order to see if this effect actually takes place in the cells, and it will be my last few slides, we had to design a particular chip structures. So we had to design a chip structure which supports very short nanosecond pulses, so has a broadband matching and a broadband capability of transmitting the pulses and delivering to the sample. And this chip assembly has to be compatible with the microscope and connectable to the generator. So this is our chip assembly and design. You can see here is the fabricated chip upside down on a glass substrate. Basically what you can see here is again a coplanar waveguide with a central conductor and the two gaps. This coplanar waveguide on this chip. This is the feeding part where we have a transition from a coaxial cable which delivers the pulse from the generator and transits to the feeding part to the chip. And then this is a specific dedicated microscope holder. So what actually what this is for is for exposing in the gap on the chip between two electrodes in the coplanar, one part of the gap on the coplanar waveguide. There are single cells which are exposed by electric field, and by having a very small gap of only 40 micrometers, we could apply reasonable voltages to get sufficiently strong electric field. Then what we found is that in the control cells, this is how fluorescent image of the cells looks like. You can see these comets. This is the normal cell. But after we took the very same cell and we apply these electric pulses, we can see that the cellular structure completely changes. And what we see here is the fluorescent. These images are images of the fluorescent signals from microtubule and binding proteins. So in short, to summarize, we showed that the nanosecond pulse electric field can affect the tubulin. We predicted that in the biophysical simulations, and we predicted that the structure of the protein can be changed. We confirmed that in isolated biomolecules in vitro, And then these insights gives us requirements for engineering design of a radio frequency chip, which enabled the delivery of broadband nanosecond high voltage pulses to the cells. And this new chip technology showed that this microchipable network, the cell skeleton network, can be remodeled completely. So what's next for us is that we want to explore the effects of nanosecond pulse electric fields on other cytoskeleton components. And in the current project, we are going to aim to explore effects of the intense millimeter waves or sub-terahertz pulses on the cells and protein components of the cell. And for these, we will need very smart and goal-oriented microwave engineers, which could design devices which will intensify wave biometer interaction. So these are just to thank our collaborators who help aid us with the biological part of these experiments. And I would like to make aware that we are currently looking for microwave engineers, particularly postdocs and PhD students. You can check it out on our website, and people who will join in our team will be working on this project, which will running for 4 more years, and with generous funding from our excellence framework for the fundamental research in our country. So with that, I would like to thank a lot for attention, and thank you very much for listening. I will check out if there are any particular questions. So thank you very much.
Thank you, sir.
Okay, I'm checking out the chat.
Okay.
Okay, great. So, okay. Okay, so may I take my my part of trying to answer the questions, or do you want to moderate this somehow?
Okay, sir. Hello. Am I audible?
Yes.
Okay, so I will ask the questions and you can
Okay.
respond accordingly. Okay,
Okay.
so the first question is when we talk about body wearable antennas, we consider permittivity for substrate materials. In biomaterials, the term become complex permittivity. What are the differences between these two?
Okay, very good question. So in general, any material is described by the complex permittivity. So, but in microengineering, we are trying to use the material substrates which are having ideally very low imaginary part of the permittivity. So, so there is only one permittivity, that's complex permittivity. That means frequency dependent permittivity, which is both a real part and imaginary part. So the real part of the permittivity, which is one which you typically consider for microwave substrates, determines basically how the material resists to the changes of electric field. So although it changes the effective wavelength in the material, and the imaginary part corresponds to the losses of the electromagnetic field in the material. So it determines how the energy of the electromagnetic field couples through its electric component to the uh, material, and how this energy from electromagnetic field is changed to the other forms of energy. So mostly it is heat, but also can be different mechanical effects. So the difference between the permittivity and complex permittivity, this complex permittivity is a more general quantity. I hope it's clear enough, or if any more questions on this?
Okay, thank you, sir. The next question is, what is the reason of taking pulse width specifically in nanoseconds, in the range of nanoseconds?
Which is the reason of taking. I'm not sure exactly what it means. So in general, there are different multiple reasons which I briefly covered. So compared to longer pulses, in nanosecond pulse, we can when we apply very high voltage, we can obtain very high electric field strength. Now, having very high electric field strength would be impossible for long pulses without heating. And since we want to avoid heating, we use very short pulses. So that's the reason why we focusing on nanosecond electric pulses. Another reason is that nanosecond pulses, because they contain, compared to longer pulses like millisecond and microsecond, nanosecond pulses, they have a lot of energy in the radio frequency band. So therefore they can be sent through the air. So potentially nanosecond pulses can be used for non-contact, well, actually they are being already used for non-contact modulation of biological functions. So potentially for treating diseases non-contactly, if I'm speaking about science fiction.
Thank you, sir. The next question is, in microscopy, coplanar waveguide different from conventional coplanar waveguide.
Okay, so basically its principle is very same. So the only difference is that the waveguide which we used is much smaller. I mean the gaps and well, even in these microscopic cases, even not that dramatically smaller. But let me show you. So yeah, so here you can see, if I zoom it in this model, so you can see the coplanar waveguide here. It transits to the chip. So major difference is that our coplanar waveguide is on a transparent substrate. So this is glass, so we can see through the substrate. It's important for microscopy. Otherwise, it's a standard 50 ohm coplanar waveguide, just modified to be useful for our purpose. And then there is a special trick that in a small part of the waveguide, this would correspond to the gap which brings us 50 ohms impedance of the line. But in order to achieve high field strength, we make a small tapering. This does not affect the overall impedance because it's very short compared to the wavelength, but it enables us to reach very high field strength in this gap. So this is the difference to standard coplanar waveguide, I would say. Okay.
Okay, thank you, sir. The next question is, what is the difference between biophysical and biochemical properties in circulating tumor cells and normal blood cells?
Okay, that's a very good question. It's more biophysical question. So there are well, biomechanics is more widely studied so far. So than the, let's say, electromagnetics of the tumor cells. In short, it's there are different types of the tumor, so I can generalize. But for I'm not sure about the tumor blood cells, but in general, tumor. So it could be some, let me take some leukemia cells. So as far as I know, they have slightly different structure. So they are typically softer. The tumor cells are typically softer than the normal cells, but there are some exceptions to this rule too, depending on the cancer type. And from an electromagnetic perspective, because of the different structure, the tumor cells of certain tumor lines compared to the healthy cell lines have different permittivity, which is mostly given by different change of the different content of the water. There are some papers on that. So if you are interested in particularly, let's say, difference of the permittivity between the cancer cells and healthy cells, I can refer you to some papers from our French colleagues who publish some data, microwave data on that. So I can, if you contact me, I can send you the paper or show you where is it. So also, what is the electromagnetic noises and how it can be eliminated? Well, it's another question which is asked here from from Raj. So if I might answer that, I'm not sure if you mean if the electromagnetic noises here. We are well beyond at least in case of the applying external pulses, we are well beyond the noise. So there is no problem detecting the pulses. But maybe you can elaborate the questions later on if you like. So I give the word back to the moderator.
I think, thank you, sir. Actually, I think this was a question out of reference, out of this context.
Okay,
Can we
okay.
proceed to next question? There is a question by Miss Komal Srivastava. Have you used coplanar in your wide experience? Have you used a coplanar waveguide feeding for body wearable antennas? How is their performance different from other feed mechanisms when it comes to millimeter wave band and sub 6 gigahertz range?
Okay, I see. So I have to admit I'm no expert in antennas. So I think unfortunately I cannot help on this. So probably I will be just saying something I'm not understand that much. We are mostly focusing on transmission lines.
Right,
So I
sir.
mean, yeah. So I think I cannot give more insight in that responsibly.
Thank you, sir. Thank you. Thanks a lot.
Welcome.
Uh, I think there are no more questions. Yes.
Hello. Sir, I have one question.
Yes, Piyush.
Yes.
Please.
Yes, sir. So my question is, when RF wave penetrate inside human tissue, how it affect permittivity of human tissue?
Okay. So you're asking if the RF signal
RF,
itself affects permittivity.
yes, sir.
Okay, that's a good question. So answer would be unless you put too much power to heat or to change the structure of the tissue, there shouldn't be. I mean, for low signals, which are typically used for for sensing or for communications, there shouldn't be any effect of the RF signal on the biomaterial itself. There should not be, right? So only if you use high powers or maybe high let's say high pulses, like for example what we did, then it can affect the permittivity.
Yes, sir. Sir, what is the role of conductivity? Conductivity of human tissue?
Well, depends on a frequency, but also how you define conductivity. We had recently a good discussion about that, because depends if you are coming from electrochemistry or from electrical engineering. So if you are speaking about losses in general, they will increase with the frequency, right? That's well known that when you go to gigahertz and to millimeter waves, then in millimeter waves, then the penetration depth, because of the losses, is only a few hundreds of micrometers. But for, let's say, in RF, being at, let's say, in a few tens of megahertz, then the penetration should be fine within, let's say, a few tens of centimeters easily. I mean, low frequency conductivity at few kilohertz for homogeneous solutions, like almost homogeneous, like blood, it's around 1 Siemens per meter. But if the tissue is unhomogeneous, then it's more complex. We need to then do some simulations of the tissue structure and how will. But then the conductivity will be also anisotropic. It will depend on the field vector.
Yes, sir. Sir, is there any disadvantage of microwave frequency or RF wave frequency on human tissue or something?
You mean disadvantage? What you particularly mean? If there is any like harmful effects or something?
Yes, sir.
Or
Harmful effect on
I see.
human tissue of microwave or RF wave.
Well, it's a good question. I mean, typically the health protection authorities, they consider only the thermal effects, only the heating, like the only effect on tissues. So given, I mean, it's always about the power, right? So
Yes,
there will be bad effects if we used high energy pulses, but those signals which we use for telecommunications or these powers, right? So milliwatts, so to say, or something like that per meter squared.
yes.
There shouldn't be any harmful effects which are like strong or immediate. Of course, there are, on long term, it's hard to say, but I don't think that there are negative health effects which will be stronger than other environmental factors. For example, drinking bad water is definitely much worse for your health than using the mobile phone. In short,
Yes, yes, because human safety is more necessary when using the microwave frequency.
yes. Well, the problem is there are the potential hotspots. That in higher frequencies you can have energy focused or not intentionally focused because of some hotspots can arise. There's a design problem that maybe you will design the device to be used for some distance from the human body, but then the device you have to also consider that there are some users might not be using it appropriately. So that's some things to consider, that having some factors to make it safe. You have to have some, you have to consider some also inappropriate use.
Yes, sir. Actually, sir, I am working on the implantable antenna for
Okay.
biomedical application. Human safety is more necessary when we designing antenna for implantable purpose.
Sure. And which frequencies do you plan to use for that?
Uh, Sir, actually, I am using MICS band and ISM band,
Okay.
which is yes, sir. Sir, is there any other frequency for implantable application which is lies in terahertz, yeah, or other higher frequency?
There will be definitely problem with absorption. So if you implant it deeper, then you will not get the signals out if in a millimeter wave and sub-terahertz, I guess. So definitely, if you want to
Yes, sir.
penetrate deeper, you know very well that if you want to penetrate deeper, you need to go to, yeah, gigahertz, sub gigahertz.
Yes, sir. Yes, sir. Okay, sir. Thank you very much.
You're welcome. If anybody from the participants would be interested, I'm more than glad to chat with you through the social media channels which I mentioned, like LinkedIn or Facebook or Twitter. Then we are all active there, so I'll be glad to answer any further questions you might have.
Oh, okay, sir. Thank you very much. Uh, so, Sir, can we take the vote of thanks?
Yes.
Yes, yes,
Okay.
definitely.
Okay. Thank you, sir. Good evening to all
Thank you
of
very
you.
much.
Okay. I, Piyush Kumar Misra, take privilege to extend a vote of thanks. On behalf of IEEE MNNIT student branch, I convey my extreme thankfulness to our Honorable Director, Professor Rajiv Tripathi sir, who has given his constant support blessing to organize this webinar. Further, I convey my deep regards and hearty thanks to Dr. Michael Cifra, who despite his very busy schedule, accepted our invitation as a speaker. We are highly motivated by his gracious presence and inspiring address. I now express my sincere thanks to Dr. Mayank Pandey, the counselor of IEEE MNNIT student branch, for his constant support for the smooth conduct of this webinar. I further thank Professor V.S. Tripathi sir, advisor of MTT and APS Society, and also convener of this event for his direction, guidance, and providing simulating environment for organizing the webinar. I now thank all the participants for their patience and cooperation who joined this webinar from different regions of the country. IEEE is a professional society for you and by you. It is your support that keep us motivated as energized. Moreover, my sincere thanks to IEEE MNNIT student branch and Cisco WebEx Meet for providing their platform. A special thanks is due to volunteers Dr. Nan Kishore, Vikrant Varsane, Pratik Raj, Saurabh Raj, Diksha, Aditya Pal, Kumar Mohit, and Vivek Rajput. These volunteers work very hard to make this event a success. Last but not the least, we thank the Almighty God for enlightening the path of wisdom for us. Thank you. Thank you, sir.
Piyush, can we hold now this photo session?
Now, I would like to request all participants, please turn on your cameras. We will take a screenshot of this for Sir, Michael sir has not joined us.
Can you see me? Can you hear me?
Yes, sir.
Yes, sir, you are audible, but I think your video is not here.
Oh, strange. Okay, I can see myself there. I will just restart the video. Stop and start. Can you see me now?
No, sir.
Ah, that's weird.
Yes.
Yeah, you know, technology. Yeah, it's strange. I can see myself still. Okay. Should be working.
Okay, sir. We are waiting.